some stats mesh?
Yeah, some stat network. I was thinking maybe it's an E-Saxon group. Have you looked in there?
Oh, okay, yeah.
Maybe that would be just the book I would try.
Yeah.
It may or may not
right.
be there. But,
the only thing is that it's, I mean, back in Belgrade, I don't.
well, they probably have a copy here somewhere.
Yeah.
And I'm not sure which of the two volumes.
That's the idea. Basically, that's what I'm thinking about.
Okay.
So,
Nice job.
in a sense, how we might interpret this kind of peculiar behavior. It can be case specific, but it can carry some information, further information.
He hasn't graduated. He's just going.
Right. He was my master's student.
I see. That's a good place.
I was hoping to.
Yeah. Well, she's a dentist. So.
No, I tried to push it.
Last time around, sorry. Blessing, as I was saying, but his student was Maryland. He likes someone.
Will dramatically increase your.
Yeah, he will dramatically increase your outside to make sure that you get good exposure. Very, very strong point.
But I think the two.
Uh-oh.
That part of it.
I just saw you have an impression.
That's why I think it would be
That would be narrow.
And maybe, because we have to instead of being miserable all the time.
Oh, that picture?
Okay, so this morning we have Simon Trebst from Microsoft Station Q to tell us about the collective states of the interacting anion, edge states, and the nucleation of the topological liquid.
Yeah, so this is what I'm going to talk about. It seems like three different topics in one talk, but see, these things are intimately related. The work has been done in collaboration with a number of people. The most recent people working on this together with me were Eddie Adorno, of course, is here, Charlotte Giels, a very gifted graduate student, Andreas Luttig at UCSB, Didier Pablon in Paris, Matthias Treuer in Zurich, and Singer Wong at Q. In Q advertisement. And so what I'm going to talk about is onions for the whole talk, and let me give you a reminder of how we think about onions. And then there's in principle two species of onions. There's abelian onions and non-abelian onions. The abelian onions are those that you learn about first when you talk about onions. Those are those 4D particles in 2 dimensions that as you take a wave function of 2 onions and you exchange their positions, this is when you pick up a fractional phase instead of plus or minus characteristic of bosons or fermions. Now, the second species of onions is the species of non-abelian onions, where the same procedure is done. So you have a wave function for a couple of these non-abelian onions. Non-abelian onions themselves span a small Hilbert space. So this wave function is no longer just in some complex number, but a vector of complex numbers in that Hilbert space spanned by these non-abelian onions. And then as you take 2 of them and exchange their position, you will, instead of multiplying the wave function by a fractional phase, make a unitary transformation in that Hilbert space by this matrix M. And the point now is that when you do 2 of these operations, you exchange positions of onions at location 1 and 3, and 2 and 3, that the matrices that you pick up do not necessarily commute. So that's one way of thinking about non-abelian onions, and I will give another way of thinking about them on just the next slide. And well, it is this species of onions that is used in proposals for topological quantum computation, which will not be the topic of my talk. So here's another way of thinking about non-abelian onions, and that is in terms of the series and examples where they appear. So here are families of non-abelian onions listed and grouped by the series that describes them. And I will describe this series, which captures this non-abelian statistics in the next slide a bit more. So here's the first group called SU2 level 2, and that is a group of Ising onions or Majorana fermions. And examples where these Majorana fermions exist are two superconductors in the context of low-dimensional superconductivity, the Moritz state as a proposal for a certain Hall state, and also in a microscopic model that is usually Kitaev and is a spin model that lives on a honeycomb lattice. The next class of onions, which is distinct from this first class, is described by a theory where this index is raised by 1, and so it's SU2 level 3. And these onions are called Fibonacci onions, and those are the onions which are present in the weak precise state, which is another state that is used to describe certain quantum Hall states, and probably some finite fractions. We had a lengthy discussion of these states last week. And there's also a microscopic model which has these anionic excitations as elementary polyparticle excitation, and it's a model just due to Letten and Wang. Now, as you raise this index in the theory further and further and further, you will eventually come to a theory called SU2 level infinity, and that's of course the same thing as SU2, and that's where we have ordinary spins as excitations, and they're only present in quantum magnets. So what I want to show here is that the ordinary spins are part of a family of non-abelian onions. They're the classical limit of these series, and they're intimately related to things like the Ising onion or Majorana fermion and the Fibonacci onion. So the theory which captures everything is called SU2 level K, where K is now an index. It's 2 here, 3 here, and it goes to infinity. So what's SU2 level K? SU2 level K is intimately related to SU2. SU2, that's what you know from the spins. And SU2 level K is a deformation of SU2, where the principal step that you're doing is looking at the representations of SU2. And as you have learned in quantum mechanics, there's an infinite number of representations of SU2, which means that there's arbitrarily large spins. In SU2 level K, you cut the number of representations representation that you allow yourself to consider, and as a consequence there's a finite number of spins, and SU2 double K, these are K plus 1, so there's K plus 1 representations in SU2 double K, and we can label them by the spin or angular momentum variable, which goes from 0, 1 half, 1, 3, and so on, up to K plus 2, giving you K plus 1 representation. Now, you can couple these representations, so if you take two of these representations, J1 and J2, you can combine them and reduce their tensor product and get a sequence of representations that are possible, just as you get when you couple two spins and you consider what kind of spins you can generate. Now, since you have this cutoff here, you want to have that cutoff also implemented in this rule, which means that you, as you couple a bunch of spins, you can never create a total spin that is larger than its cutoff spin. Now, it's probably a certain amount of dryness in here. Let's look at an example. So if K is equal or larger than 2, there's a rule in these rules, which are also called fusion rules, in the conduct of the anyons, which reads 1 half, and 1 half is 0 plus 1. Now that is, of course, very reminiscent of a spin 1 half, and a spin 1 half coupled into a singlet. And it's exactly the same thing, only that there's no degeneracies in anyon length, so there's representations on halves that can be coupled into 0 or 1. As you increase this level in the series, if S equal to K and K is larger or equal than 4, you get a rule which reads a 1 and a 1 going to a 0, a 1 over 2. And that, of course, is again reminiscent of two spin 1s coupled into a singlet to spin 4 quintuple. Okay, so these are the series of non-abelian anyons that I want to look at, and let's reconsider those examples that I talked about and see how they play out. The first one is one of a Karl Heber superconductor. So here's a superconductor, and in the superconductor there's two kinds of excitations. There's a vortex excitation, which is called sigma, and there's the Bogoliubov quasiparticle, the fermionic excitation of the superconductor, which is called psi. Now, these Greek letters are just other names for those angular momenta that we looked at before. If you take two of these vortices, there's a characteristic rule. Two vortices, a sigma and a sigma, can go into a state 1, which is just a superconductor, a vacuum, or they can form one of these quasiparticles, the fermions, that can go to the fermion. So this rule is exactly that rule that two spin 1 halves can go into a singlet here or just here. Okay, so the theory that describes the vortex excitation in the period superconductor is SU2 level 2. There's a nice paper by Reed and Green giving all the details. Good. So that's one example. Another example, which is closely related to that, is a quantum Hall set at a certain filling fraction by a part which I've heard about in this program probably quite a lot. Probably the best candidate for the function today is the Pfaffian set of Warren Reed, which again is described as this topological theorem of SU2 level 2. So the quasiparticle excitations in here would be Ising anyons carrying a charge D04. Now, much debated last week was a question: what's the best wave function for the 12th state? It might be the para-fermion state of Reed and Mazar, but it might not. If it is, then it is described by SU2 level 3 and the elementary excitation of Fibonacci anyons. So my interest is not so much in discussing which state is truly occurring at the 12th plateau, but what the physics on the plateau would be if we allow for basically any of these non-abelian series. So what I want to consider is the following scenario. I'm taking my topological liquid, and I'm looking at this liquid, and there's a bunch of excitations in there which now carry a certain non-abelian quantum number, one of these generalized quantum spins that we have looked at in this series. I would like to ask, given that you have now these anyons, what is the collective state that these anyons form as I allow them to interact with each other? And I would like to ask this question in two ways. One way is, what is this that is happening with in this quantum many-body problem of many anyons? And the second one is, I would like to understand what consequence that has, this collective behavior on the original liquid, which is the SU2 level K liquid, of which the anyons are excitations. So let me be a little bit more precise of what I would like to look at. So I start this in Ac2OK liquid. I put in a finite density of anions. So not just a pair, but really many. It's a macroscopic population of that liquid. And the positions of those anions are going to be fixed, so they're pinned to a certain location in space. And their distance might be described by some characteristic scale, so I call this A here, and I want to compare that scale to another characteristic scale of the system, and that is the correlation length, so the magnetic length of the system or the coherence length of the superconductor. Now, if the spacing of the anions is very large compared to that characteristic scale of the liquid, then despite the fact that the anions are at fixed position, there's a degeneracy of the state that these anions can spin, and this macroscopic degeneracy is basically perfect, so there is no splitting whatsoever. And it is this state, this Hilbert space of degenerate states that is then used in these proposals for quantum computation. Now, if we push the anions closer together, such that this distance between anions is no longer much larger than the characteristic scale of the liquid, then the degeneracy is going to be split. And a certain state is going to be the lowest state in that split Hilbert space, and we would like to know which state that is, and characterize it to the best way we can. Okay. So what is the collective state? Here are a bunch of possible scenarios. The first one is to take an original liquid, and some interaction between the anions prefers two anions to pair up into something like a dimer. So that would be a gap excitation, and that wouldn't affect at all the underlying Ac2 locality, so the underlying topological liquid. So that would remain unchanged. Another possibility is so this possibility, we will black that out in the end, but for the time, let's consider it. So another possibility is that the anionic degrees of freedom form a collective state that is gapless, and as such, we get a liquid which is different from the original liquid, which is a gap topological liquid. So there's no gap in this, no gap in this liquid. That is a scenario that is, to some extent, reminiscent of what happens for ordinary spins. So if you take ordinary spins and couple them antiferromagnetic on the scholastic, you get a Néel state. That would be the Néel state. So that's a possibility. If that happens, there is a distinction between the original liquid and the new liquid, and they're different. Well, this is a gap one, and this is a gapless one, so nothing terribly important has to happen at the interface between these two liquids. That is different if what happens to the anions is that they form a new liquid that is distinct from the original one and also gapped. So if you get a gapped quantum liquid, as the collective state of the anions, you will have is some new state here, and then there's an edge state which runs around the new nucleated liquid and the original liquid, because as two gapped liquids touch in space, there must be a gapless edge mode at the interface between the two. So these are the three possible scenarios that I could come up with. You might have many more in your head, and so let's look at what really happens. So to do this, we have to introduce an interaction, and we want to do this first in a rather abstract way, and we follow an idea that has worked very well for ordinary spins. So as we looked at these fusion rules, and we said that two of these anions carrying generalized angular momentum 1/2 can couple into a state 0 or 1. Well, in the land of ordinary spins, where two spin 1/2 can go into a singlet or a triplet, the effect of an interaction is that these two levels are split by some tunneling process, which is a microscopic thing that we want to ignore. Splitting these things these two fusion outcomes, you can write that down in the context of a Heisenberg Hamiltonian, where we project onto one of these two outcomes. So the Heisenberg Hamiltonian in ordinary spin length is typically written as the sum of pairs I and j. Si as j is nothing but a projector onto a single channel. So we can do the same thing here for the anions. So we can take one of these two channels and energetically favor fusion into that channel over fusion into the other channel and introduce a characteristic scale, a gap, for the splitting that we call J. And as you write on this Hamiltonian, we run over all pairs I and J of anions in this liquid and have such an interaction. Now, that's the abstract way of approaching this problem. And then there is a microscopic way of doing this. And that is actually calculating the splitting J for particular examples. And well, this has been done rather recently by a couple of people also present in this room. And so let's look at this microscopics. First of all, there's a nice paper by Parser Bonderson, which doesn't give you the microscopics for a particular fluid, but tells you that this splitting is due to topological charge tunneling. So he can write down the exact process that is relevant for this splitting in the same way that we can think of it in the context of ordinary spins by some virtual tunneling process. Now, let's go to these examples, which are real calculations for example, fluids like the P-wave superconductor. So Shankar-Dasama's group has looked at what happens if you take two of these sigma vortices in the P-wave superconductor and change the distance between the vortices and look which of the two channels that these two vortices can couple into, the conventional superconductor or the boule of quasi-particle fused into. And what they find is that on a small scale, these two vortices prefer to go with the superconductor and not the boule of quasi-particle, but actually as a function of distance, this splitting oscillates in an exponential envelope. And it's quite interesting to see that that is different from what happens in the Moritz state. You take the Moritz state and you put into quasi-holes, and then it's a calculation that has been done by Steve Simon, Nick Bonsi, and others. You take two quasi-holes, which also create a spin on half, and you bring them close to each other. They like to go into the fermion state, so the state 1, which in the language of Greek language is called psi. So they choose a different channel, and then the same physics happens as you increase the distance. There is a characteristic oscillation on the scale of the coherence length or magnetic length, and all of that happens in an exponential envelope. And similar to the P-wave superconductor, there's been a calculation for guitar as honeycomb lattice model by Ville Latin and Janos Bachhaus and others, where they find the exact same thing as in the P-wave superconductor. Two vortices close each other, refer to the trivial channel, and then as you increase the distance, there's an oscillatory behavior, like you also favor the other channel. So what we learned from these microscopic calculations is, well, that the whole detail now sits in these examples, but the answer is not universal. So you get both answers on similar scales, and you have an oscillatory behavior, which means that for every single example here, there's characteristic distances where you prefer the one channel or the other channel. So we will be interested in considering both cases of coupling signs in our example. So if you write the projector as a projector into a single channel, we are interested in J being positive or negative. So this is the microscopic input, so this gives us a number for the splitting. Let's assume we have some, and now let's go to abstract land and ask what is the resulting state that we can get if we consider such a Heisenberg Hamiltonian. Writing down a Heisenberg Hamiltonian is a very powerful thing, because now we can ask all kinds of questions, as they have been asked in the solid state. You can ask, what happens if J changes sign, if J is some distribution of signs, if the regularization of the lattice that you're looking at has a particular type, like triangular lattice or Kagome lattice, things that are really interesting in the context of ordinary spins. In anion land, we tried to do this also, but started with the simplest possible example that you could come up with. and that's chain. So what we're interested in is really trying to do the simplest thing that we could think of, and that is we take a two-dimensional liquid, we take a bunch of excitations, but we align them in one-dimensional space, but there's still excitation of a 2D liquid, and we put interactions between neighboring pairs such that they all interact with the same strength. So we look at this mostly in the context of SQ2 level 3, and that's why we phrase it as the golden chain, because there are so many golden bits to show. So let's look at this particular example first of a one-dimensional system of interacting anions. It's a particularly simple one, and we can do a lot of things, and at the end of the day solve it. Exactly. So let me flash on half a slide the technicalities involved in doing this. So what you need to do is, when you have such a chain of 1/2, so spin 1/2 degree of freedom, which you call tau here, you would like to write down some Hilbert space. It's quite distinct in doing this for the anionic case as compared to the ordinary spin case. What you might want to consider is a so-called fusion path. You take these anions and you fuse them along some line that you put through your system of your own choice. And then along this fusion path, you start fusing the anions one by one and start getting different labels along the fusion path. And these labels on the fusion path, which are ones or taus or spin 0, 1/2 or 1, those labelings are then the Hilbert space that span all the beta states. Okay, so this is a particular choice of basis. You could have chosen a different one. And what allows you to go back and forth between different choices of basis is a generalization of the six-channel symbol that's called F matrix, and the Hamiltonian for chain, and then you've written the sum of local terms when you do a local basis transformation you project onto your favorite channel, which in our case is the single channel, and then you do the inverse basis transformation, and so that's the Hamiltonian. There's really a lot of technicalities in doing this. I don't want to talk about it, so if you have questions, you can ask me after the talk. Let me give you some results for these chains. And the first result comes from Americs. That's following the historical path of how we did these things. So let's look at the left-hand side. When we look at the finite size gap, so we take a system of length L, which means that we take a system of L of these anions and we diagonalize it on a computer. And because it's a finite system, there's always a finite size gap above the lowest energy state, the finite size energy gap. And this is plotted over here. So what you see here is this finite size gap as a function of inverse system size. So small systems are on the right, and larger systems are on the left. And as we look to the left, we extrapolate to the thermodynamic limit. So we start here somewhere with 10 anions, and then here we have 200. And this allows us to very well see that the dynamical critical exponent of these lines, which correspond to even and odd length chains, is exactly 1. So it goes away, this finite size gap is 1 over L, which has the implication that in the thermodynamic limit of an infinitely long chain, this chain is going to be gapless. It's described, because it has this dynamic critical exponent of 1 by conformal field series. So one way of describing this theory, so this gapless theory, is by characterizing the conformal field series through its central charge. And one way of doing that is by looking at the entanglement entropy of a system block to the whole system. And so we have done this, and it's plotted here. We follow this scaling equation by Reza, and what we find is that that central charge is 7/10. So that's an old friend. It means that the conformal field theory describing this chain of the anions, in this case Fibonacci anions, is a tridimensional Ising. So when you see things like this happening, it's a very simple theory. You might guess it. There's a way of describing these systems even better, that is by solving the system analytically. And this is indeed true for these chains. You can solve them exactly by mapping them to something that you have already studied before. So if you look at the terms in our Hamiltonian, so those local terms that favor projection onto a particular fusion path, it turns out that these terms in the Hamiltonian, as you multiply them by a factor, form a certain algebraic structure, which is called the Temple-Leap algebra. So, these operators have exactly these properties which define the Temple-Leap algebra, and there's one free parameter in that algebra. This well, sometimes called the isotopy parameter, and in the example of these ionic chains, this parameter is exactly the quantum dimension of the Fibonacci of the anion that we have put in. So in the context of Fibonacci anion, that is the golden ratio. In the context of Majorana fermions and P-wave superconductor, this would be square root of 2. And in the context of ordinary spin, this would be 2. Now, with this algebraic structure in mind for the Hamiltonian, you can take your 1D quantum Hamiltonian and map it to a 1 plus 1 dimension system, so you can look at the transfer matrix. And what you find is that that transfer matrix itself is an integral representation of the RSOS models and restricted solid-on-solid models. So once you look at the transfer matrix, you realize that the transfer matrix itself is solved exactly and it has been done before. So at this point, we're done. And you can pull out the solution from the restricted solid-on-solid model and write it down in great generality for all kinds of levels. So remember that we consider the SU2 level K liquids, and the anion that we put in there is a spin 1/2. So you can now categorize all these series for different levels. So we start with 2, the Majorana fermion, 3, the Fibonacci anion, and go on up to infinity, which is the ordinary spin. And then there's 2 couplings. So these 2 spin 1/2s can go into the trivial channel, the 0 channel. That's the one called antiferromagnetic, similar to the ordinary spin system. And then you see how these series evolve. So the gapless series describing these chains. For level 2, it's an Ising series. For level 3, it's a tricranial Ising series. For level 4, it's a tetracranial Ising series, and so on. So you can see the pattern. For level K, it's a K critical Ising series with this central charge. And then as it takes a minute to infinity, you recover the Heisenberg antiferromagnetic with central charge 1, as you should, because in this interacting system comes the Heisenberg chain for large K. Now, there's a second family of series, and that is the one that you get when you have these 2 spin 1/2s being coupled into the high spin. So 2 spin 1/2s go into spin 1. That's what we call the ferromagnet, because in the limit of K to infinity, you will recover the Heisenberg ferromagnetic chain. So these series are different. So they're not at level 2. So we start again with an Ising series, and then for level 3 is a 3-state box model, and level 0 sequence, which at level K is a series of ZK parafermions with a characteristic central charge. And as you extrapolate that to infinity comes 2, which is correct. Also the ferromagnet, of course, is a number of that, and it's not the form.
Can I ask what statistics here? So I mean, when you go down this line, I get more and more complicated anions, and then the limit, I guess.
So as you go down this line, your SU2 level K allows for more and more and more spin representation, but we're always looking at chains which are built out of the elementary spin 1/2, so the lowest spin. And they can couple into larger and larger spins. Nevertheless, the family of models is always a spin 1/2 chain. Okay? For larger Ks, you could have generated more complicated chains, spin 1 chains or spin 5 chains. Those are not considered. So this is really the simplest version of this. Yeah? And that gives you this family of series. But there's as you go to larger K, there's other gapless series like spin 1 series and spin 3/2 series and so on. So it becomes a rather diverse but what is nice, so here there's an example of an interacting system, which you now connect an interesting system of Majorana fermions to an interacting system of ordinary spin 1/2. So that's a nice conceptual step, going away from just connecting the degree of freedom, but now we connect the whole common body system. So that's in this table. Now, the series can be written in a slightly different way as well. So this K-critical Ising model is the same as the minimal model, the case minimal model. And the case minimal model is sometimes written as a coset in formal field theory. And since we're going to employ this coset description in the second level of this talk quite a lot, let me run it by you already now. So the K-critical Ising theory has a representation which is SU to level K minus 1, SU to level 1 over SU to level K. And similarly, the ZK parafermions can be written as SU to level K over U1. What I would like you to notice already here is that the theory describing the original liquid SU2 level K is part of both cosets. Now, before we go into that coset description in more detail, another thing might come up, and the suspicion. These are all critical series, and they become more multi-critical as you increase K. So you might think that these are series that are not at all stable, and it is sort of a lucky coincidence of fine-tuning that we actually see them. Like level K, you can already have intercritical Ising model. There's tons of relevant operators in those series, and you would think that as you slightly deform your system by varying, for example, the interaction on some of these points, you would no longer see these series, and you would follow these multi-critical points. It turns out not to be true. So what these arrows indicate is that all of these series have an additional symmetry, which we call topological symmetry, but which really is the effect of taking such a chain and commuting a spin through the chain and looking at the eigenvalues that symmetry operation can have, and seeing that that symmetry stabilizes these multi-critical phases. So what that means is that despite the fact that there is tons of relevant operators in these multi-critical series, they're all symmetry forbidden by that additional symmetry. That symmetry is a symmetry that is present only in the anionic series. It's not in the ordinary spin case, and as such it doesn't work there. But what we find is that these series are all remarkably stable, so it works for arbitrary level of K, and from the perspective of a microscopic model, it looks extremely suspicious probably, and we will see in a second a much more physical way of understanding why these multi-critical series are indeed very stable.
So may I ask? So are you claiming, for example, take the Moore-Reed as a background liquid to this? So if you would go beyond the lowest order coupling and include, let's say, next nearest neighbor coupling that comes from that background, would it respect this symmetry? Or would it,
yes. So exactly that's the point. So if you were in the Moore-Reed state and you had a bunch of Majorana fermions here, and this is a simple model of a chain where you have only nearest neighbor directions, and you get this theory. Okay? And now you also introduce a next nearest neighbor coupling, and there's a tunneling process, of course, which will do that, but it's going to be weaker. The statement is exactly that. The next nearest neighbor coupling tries to couple to a certain relevant operator in the theory. It's going to be a forbidden, symmetry forbidden relevant operator. So it's not going to gap this theory out. Okay? So, and this is true for all kinds of things that you can do, like randomness in these chains. So you can start whittling down the position of these onions, and it's not going to change the critical theory. So this seems quite remarkable, and it's not the case in the ordinary spin space. The ordinary spin case is quite different. First of all, there's no relevant operator. So in the Heisenberg chain, there's only a marginal operator, and so that's different from this. Here you have relevant operators en masse, but you're unable to couple to them. Because those relevant operators all live in sectors which have a certain flux going through that chain. If it's a periodic one, you can nicely see that. And threading a flux through the chain is a non-local operation. But the next nearest neighbor coupling is not non-local. So there's no chance of actually doing that, and as such, it doesn't work. you will see why these things are so stable in just a second. And that's connected to the idea of edge states.
Is it obvious what happens if I flip the sign of just one bond or something?
Yeah, so we're just in purity state, so that's not going to do anything. Pretty sure that's a statement.
So if you flip the sign of one bond, it's not going to
do anything. Yeah, so you're not able to, by this local operation, to destroy one of these series. Yeah? So this might sound all very abstract. I didn't want to talk about the symmetry in detail, but it's more mathematical. Then the picture that you will see in a second, which connects these series to edges, and then you will see why those edges are actually stable.
This sort of in general destroys that symmetry in the sense that you go to the random singlet phase.
No, that's not true. The random singlet phase that you have in mind is strong disorder.
Right.
Yeah? The strong disorder is infinite randomness, and it's very far away from this scenario that I'm talking about. I'm talking about weak disorder. Yeah? The strong disorder means that you have an exponential variation in those couplings. That's a very different scenario from you flip the single one or you vary a single one a bit. Yeah? So the random singlet phase is a very different piece there. So let's look at this connection of these Kepler's nodes to edge states, and that will shed some light on the stability issue as well. So what we have seen so far is that we took our original liquid and we placed a bunch of anions in there. We put them on a line, we had them interact, and then we find a gapless theory describing the collective state of this chain. Now, that theory was given exactly in this coset form, and now let's reinterpret that coset in the following way. So you get a gapless theory that lives on this chain, and now let's split that gapless theory into a right-moving part, and right here in the left-moving part, also right here. But I separated them a little bit in space so that I can put some yellow in between. The yellow is supposed to indicate a different liquid, a liquid that is distinct from the original SU2 level K liquid. And now let's see how that occurs. So here is what we start with SU2 level K. Then you get a gapless theory, which you have split into right and left moving parts here, and which is described by this coset. Now what that coset tells us, that it is the boundary between this theory and that theory. So the liquid, the yellow one, which lives between those right and left moving series, is this. So the upper part of that coset. So what this has is that the effect of a finite density of interacting anions has the effect of nucleating a new liquid within my original topological liquid, which is distinct from the original one, and as such it must be separated from the original gap liquid by an interface which is gapless, and this gapless interface is just a theory that I have calculated when I calculated this chain. Okay, so that's the idea. And I will spend the next, 30 minutes or so on motivating why this is true. Of course, what I've just said is not, it's a theory construction. I've made a left and right moving mode and then separated them in space, something that I'm not supposed to be allowed to when I do a 1D calculation, talk about a two-dimensional configuration. Nevertheless, this conceptual picture already allows us to answer this question.
So what implication would it have in the P plus IP? Could you actually, in principle, nucleate a bunch of vortices and you have some edge state?
Yeah. So.
And what's the nature of that edge state?
Yeah. So actually, I think I have it. Well, I on the next slide I have the next example. I can translate that one step down. So already now we have. Whether we believe that this construction is true, that there is a new liquid that is nucleated, we have found a way of calculating an edge state. So here I steal the example that you will hear about tomorrow from Caroline. Let's take an SU2 level 3 liquid, and just plug the 3 in all these equations with K wars, and then we get all these edge states, which are SU2 level 2 plus SU2 level 1 over SU2 level 3. That's the 7/10 crystallizing theory. So the nucleated liquid has this form, And now I can just take the lower left, lower half of this picture and plot it like this. So I calculate the interface that I get when I bring two of these liquids in spatial proximity. So here is the edge between SU2 level 3 and SU2 level 2. I take this SU2 level 1 and put it on the edge. So then I get this triangularizing edge. Now, that's going from SU2 level 3 to SU2 level 2. And what you're asking is what happens if I take SU2 level 2 terminal interaction. So I would have SU2 level 2 here, and on the other side I would have a U1. So here,
SU2 level 1.
what happened to that? I moved it on the edge as a U1. Okay. Okay, so that's just to have those two limits that I would like to describe on the left and the right side of the interface. Okay. So this is the example that we get for one particular coupling sign, and well, there are two. Let's look at the other one. So this is the edge that I can calculate for what we call antiferromagnetic coupling. So two vortices going into the trivial channel. If the two quadrupole excitations come in the other channel, the ferromagnetic channel, then those critical series where the k parafermions, which in cosine are written as S to the k over U1, and now we can do the same interpretation again. Well, this describes an interface between SU2 level k and U1, and we have this theory living on the edge. Yeah. So this is an interesting observation. What it tells you is that there is a difference in what it means to go into the low spin in the antiferromagnetic channel and going into the high spin in the ferromagnetic channel. And that ferromagnetic channel, the effect for all levels of K's for this liquid are that you nucleate a new liquid, which is U1, which is abelian. So you have reduced your non-abelianness completely to become abelian. While in the antiferromagnetic case, you have seen these minimal models, which means that SU2 level K becomes SU2 level K minus 1. So you go also down in non-abelianness, but only one step. Yeah. So if you were at SU2 level 5, you would go to SU2 level 4, and you could do this construction many times.
Can I back up to my previous question? If I flip one of the signs of one of the bonds, it seems that I break it up into two halves. So if I flip the sign of one bond, you said it doesn't do anything, but let me flip the sign of two bonds. Now I have edge, I'm starting to nucleate a liquid of a different type with edge states that counter-propagate. It's hard for me to imagine that flipping the sign of one bond isn't going to break the liquid up into halves.
Into two. Well, so all these theories are, of course, for the infinite system. So again, so yeah, so I would have to think, what that one bond, is supposed to be as an operator, and see what it does. Okay. So now we have gone through an argument where we have connected the gapless series on these chains to edge states, and also to the nucleation effect of a new liquid. And it is the second statement that is probably the one that one should consider more deeply and ask whether it's really true. And so what you really want to do is a two-dimensional calculation instead of a one-dimensional calculation. So let's try to do that. And like in the 1D case, look at a simple lattice regularization of the quantum many-body system with this one. You take our anions and you put them onto a square lattice. And then we have already seen what would happen if in the square lattice you would couple only the anions in the horizontal direction, forming these chains, and in this picture you would result in a scenario like this. You would get slivers of the new nucleated liquid surrounded by edges, and well, this happens for every horizontal line in this picture. And now as a next step, you couple these anions in the vertical direction, so we start coupling between these slivers of a liquid, and what we find is that, this is what happens, you get one big bubble of a new liquid, which is the same, so the color is supposed to indicate as the one that you would have in this 1D calculation. So this answers this question already to some extent. If you have a two-dimensional array of ions and you let them interact, what you nucleate is a new topological liquid which is gapped and distinct from the original one. So that also has the implication that there is an edge state between these two liquids. So from my three possible scenarios in the beginning, that's the third one. So how do we know that this is what's happening? So, well, we have studied exactly this system, which in the context of ordinary spins has been studied a lot, so ladders and leg ladders. And so here are two things from those studies that I want to highlight. You can study this limit. You take two chains, and they're originally decoupled. And so this system of two decoupled chains is described by conformal field theory that is constructed out of the conformal field theories describing the single chains. It turns out that that theory is not just a simple tensor product of the conformal field theory of the individual chains, but it's slightly more complicated. There's certain operators that you might be able to construct which are not present in those theories. And then you can analyze the conformal field theory describing these two chains and look which operator is the most relevant one in that theory. And it turns out to be the one that couples actually the two inner edges. So this right moving edge to that left moving edge and gaps them out. As you do that, you end up here. So that's just a cartoon for two chains, and then you can repeat this for many, 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 and get the same thing. Now, this new liquid that is nucleated is a topological liquid, and as such, because it's a gap quantum liquid, as such it is sensitive to the manifold in which you put it, and in particular to the boundary conditions that you might choose. So we do the following numerical experiment. You take this liquid, and while we have periodic boundary conditions in the chain direction, we play with the boundary condition in the wrong direction. So if this boundary is an open boundary, there is an edge on the top, and there's an edge on the bottom. So, and you can calculate the energy spectrum, and as you do that, it's not the most impressive energy spectrum that you've ever seen, but you can actually fit it to a conformal field theory, which is a conformal field theory that you have already seen for the single chains. Now these systems, because they're two-dimensional, and this is all exact ionization, it's getting smaller and smaller and smaller, so the finite size effects are getting larger, and it's not as impressive as doing very long one-dimensional chains. Now, as you take the wrong direction and make it periodic, what we see is that that spectrum changes dramatically and becomes a GATT spectrum. Okay? So before we could actually fit it to a conformal field theory, after that we can no longer. You might probably need to be an expert in seeing that. One way of seeing that very quickly is if you look at these lowest fields, which correspond to the operators of the conformal field theory in the left spectrum, you see that there's exact degeneracy between certain states here, which you will not have in the conformal field theory, in particular the low states. Totally degenerate. There's a gap here. Scale of these two plots is slightly different. And what is important that you see actually degeneracy occurring in the low energy sector. And for this case, what we have calculated is the two-dimensional areas of Fibonacci anions. So that's SU2 level 3. And that nucleated liquid here is SU2 level 2. And as such, it comes out exactly right that these three states as near ground states, those are exactly describing SU2 level 2. So that's the numerical evidence that we can generate by looking at these systems of interacting Fibonacci anions. But we can also take all these results, these conceptual pictures, and try to fit everything that you've ever heard of into this context. So earlier work, and it turned out to work very nicely. So in particular, there's all the examples for interacting Majorana fermions. So Niedried and Andreas Ludwig have been way ahead of their time in looking at the weakly disordered case of Majorana fermions and find exactly the effect that we described. You go from an SU2 level 2 liquid to a U1 liquid if all those minimum interactions have one particular sign, which we now call ferromagnetic. And it also nicely fits into the calculation that Ethan Wilson and Arne Stern have done for Majorana triangular lattice. For SU2 level 2, the square lattice is special, so the more generic case is a triangular lattice. Where starting from a weak pairing superconductor, they see that the effect of interaction gives you a strong pairing superconductor, fully in agreement with this picture, as we said before. Alexei Gitaev has looked at this example as well, never published it, and there's some more recent work by Michael Levin and Bert Halpern along these lines as well. And then people in this room have been thinking about Fibonacci anions, so looking at the next level of non-linear series. And so Karl-Jan tomorrow is going to talk about this scenario of having an SO3 level 2 liquid and an SO2 level 2 liquid being nucleated by interactions in this case, which again fits into our picture. And Sander Bezos, again, similar construction and coupling with an edge state, and it all fits in this picture, which is very nice, because now we have made a very powerful correspondence between the collective state of an anionic spin chain in one dimension and the edge state that can occur at the interface between two topological liquids, and then use that as a physical mechanism to describe the nucleation of a new topological liquid as an apparent liquid, and you consider the effect of a finite density and interactions between anions. That's a serious paradise, because this is probably what is very interesting, this two-dimensional nucleation effect, that we can calculate all its properties by doing a very simple calculation in one dimension. Doing calculations in one dimension we are particularly good at, because conformal field theories at our hand. Many numerical methods are much more powerful in one dimension than they're in two dimensions, and this is how we can actually get a grip on this hard problem of two-dimensional interacting anions by looking at their one-dimensional counterparts. Yeah? The reason that you can go from one to two dimensions is that the collective state that you identify is a simple one. It's a gap one. And connecting in a dimensional reduction a gap state in 1D to 2D is something that is not too exciting, and as such it actually works. Yeah? This should not be confused with the fact that we also see a gap that's low, but that's just the edge. So, having all this in mind, we can now translate those calculations that people have done microscopically by looking at these interactions between two vortices in a p-wave superconductor or two quasi-holes in the reed state, or two vortices in the p-type model, and translate them into this liquids picture. So which liquids will these people find? So here it is. Now, it turned out that, of course, these series describing these particular examples are slightly different. So this is a fermionic quantum Hall wave function, and this is a bosonic one. So we have to take care that when we write this 2 level k, we get our U1 factors right. And it turned out that we get different liquids. Unfortunately, in the case of SO2 level 2, everything is special, and all these liquids carry the same name. They're called all U1. Indeed, they're actually different in their binary representation, for example. So the point here is that I want to make is that we can now translate the pair calculation to, what is happening to the splittling of a pair of non-abelian ions into the collective quantum body state. And
I'm going to ask a question, but as long as I'm asking a question, I'd throw in my usual comment. The calculation for the T-wave superconductor, it's not done by that article. I don't think they even claim to do it.
Yeah.
But my question is in the don't I expect it in the two phases to actually differ by the direction of the edge state? I mean, the U1's different in the direction of the edge state, or did I misunderstand that?
Whether this arrow is pointing this way or that way?
Yeah.
So I probably have not carefully thought about that when I was drawing these cartoons. So here's a very careful table. So where we now translate all these, going from SO2 level k to SO2 level k minus 1 and taking care of all these U1s, so you can do that. And you can look at the bosonic kind of the fermionic superconductor, and then you just take care of this U1 in the right way, and then this is a point. Okay, so we can write that down explicitly for all these cases. Okay. So there is no difference between the story in a bosonic quantum hole or fermionic quantum hole, just of getting your U1s right. Okay, so we can look at this table again if you're having a more detailed question. Okay.
Can I ask, perhaps you said it, but I missed it. Is there some critical density of these things for this to happen?
Yeah.
I mean, because if we just put a few forward you see nothing happens.
So the answer is the critical density is 0. So once you put in a macroscopic number of vortices, a finite density, yeah, then you're dead. Any finite density, you're dead. Yeah? So what we find is that the liquid is unstable. There's a relevant perturbation which nucleates the other liquid at 0 temperature. Now, How does it, work with other concepts of, topological liquids being stable? Well, putting in a vortex is a topological excitation. It's a very different thing than those local perturbations that we're talking about when we talk about, the stability of topological phases. So putting in a finite density of vortices in a topological liquid is a dramatic topological change, and as such it destroys the topological feature. Now, let me give you the example of where I think all these things are going to be relevant. So here's a quantum Hall plateau, and here's the middle of that plateau, and so this is a magnetic field direction, and now I detune the magnetic field a tiny amount from the middle of the plateau, and depending on the direction of that shift, I will start populating the original quantum Hall liquid with a bunch of quasi-holes, for example. And then the quasi-holes and the contact of these quantum holes, they carry a charge, and there's electrostatics between them, and the electrostatics will force these quasi-holes to form a weakness crystal. Now, the spacing in that weakness crystal A is going to be very large compared to the magnetic length of the quantum Hall liquid for slight detuning on the middle of the plateau, because the density is just very, very low. But as you further move on that plateau and detune the magnetic field, you will put more and more vortices in it. As a consequence, the spacing in the weakness crystal is going to be smaller, and it will become of the order of the magnetic length, and that's where you have the transition into a new liquid, and this is going to happen on the plateau. Now, when we do these quantum Hall studies, we don't do them at 0 temperature, and that's why I draw that this position first only here, because we're at finite temperature, and we have to compare all these energy scales to that finite temperature. At 0 temperature, strictly speaking, this transition occurs immediately, as you will also need to plateau, because the smallest finite density at 0 temperature, and Steve's calculation shows us, there's an exponentially small interaction, but there is an interaction that has this effect. Now here's a speculative part. As you walk off, you see magnetic field on the other side of the middle of the plateau. What we're doing is you're putting in quasi-particles. So we don't know whether quasi-particles are fusing in a different or the same channel in a density as the quasi-holes, but simply by observing that quasi-holes and quasi-particles are not symmetric, so there's no particle-hole symmetry here, we might think that they're actually going in a different channel, so we don't have them. If they were, you would actually see a different effect on the other side. So as you detune here magnetic field in this direction, you will also nucleate a liquid, but it might be a different one than the one you see lower magnetic field. Okay? In both cases, you would see the effect of this if the quantum Hall plateau is wide enough, such that you actually see the spacing in the weakness crystal becoming so small that it becomes of the order of the magnetic length. That is a microscopic question again, and needs to be calculated for a particular example. And in general, I think that is.
So presumably this is all fine if all the couplings are the same sign, and if there's
well, so in the weakness crystal, all couplings are identical because all distances are exactly.
If it's a disorder free. Well, but I mean, I have second year's neighbor coupling, which I have to worry about, which could be of an opposite sign.
Exactly. So that's but that is exactly the case that I described to Caroline in the case of the 1D system. Again, so the second nearest neighbor coupling is that's your own calculation going to be exponentially smaller than the first nearest neighbor coupling. It might have a different sign because you might have gone through the installation, and as such it has some effect, but it's going to be not a relevant perturbation to the case, and that's you see that immediately because this liquid is a gap liquid, so you turn on your favorite perturbation. That favorite perturbation is going to it's not going to destroy that gap. But if it doesn't destroy the gap, you're not destroying this liquid, and you're not destroying the edge state. So this is a point where you again see why in those microscopic series, these multi-critical series were amazingly stable, because they're describing the edge state of a gap liquid. So any perturbation that you introduce, like a next nearest neighbor interaction, is not powerful enough if it's small to destroy that gap, and as such, any multi-critical series living on the edge can be destroyed, and as such, it's very stable. But sorry.
But I think you're assuming here that the quasi-particles are actually pinned somewhere on impurities, so it's rather unlikely that they're
so as I said, the mechanism that I'm having in mind is the formation of a weakening crystal due to electrostatics. There is a point in saying, well, there might be impurities and they have a pinning effect on themselves, and that's true. So there's actually interesting physics connected to it. Yeah?
But if the quasi particles are mobile, then you will actually get charge transport because of this whole.
So let's step back. So what did I say? Why I think that this is what's happening. So as you go off the middle of the plateau, you start putting in quasi-holes into the hole liquid. Those quasi-holes carry electric charge. The electric charge then has the electrostatics will then have a strong interaction between these guys, and it's the electrostatics that forms the weakening crystal. Yeah, those interactions in the charge sector are the ones that pin the quasi-hole to the weakening crystal locally positions, and impurities might pin as well if the impurity pinning force is larger than the one coming from the electrostatics. The interaction that is responsible for forming the weakening crystal is a different one than the interaction in the non-abelian sector that I'm considering when I talk about this nucleation effect. So that's a different. But you are right. Impurities might start distorting this weakening crystal, and that might have dramatic effects, and that's true. So that's again coming back to those microscopic calculations. As you start wiggling around the position of an anion in the weakening crystal, the nearest neighbor interaction might be dramatically changed because you're living in an exponential envelope, and as such, this whole picture might not be applicable at the end of the day, but it's a picture already, which is good to also describe that case. So what is happening if you have strong randomness? And we can talk about that probably after this talk. So I have my own personal idea of what might be happening, but it's nothing that we can calculate as coherently as this. So to some extent, this might be too much of an abstraction, but it's a good first attempt to describe what's actually happening on the plateau. Okay. So let me.
Can I ask one thing there? I mean, wouldn't you think that the first thing that, since usually, say, in answer to development, you have to create these things in pairs. You cannot just put in one. So isn't it physically what would happen when you start to move away from the plateau that you would be more likely to nucleate Laughlin kind of quasi-particle and charge a half quasi-particles instead of the quarter? At least you would have very strong correlations when this thing starts to
that would be true, then you would see even other effect.
Yeah,
of course, I'm not claiming that this is the even effect they're seeing, but you can have similar arguments
because you
there
cannot just pop up quarter charge impurities in this liquid.
Well, so that's the question. What happens exactly when you detune? So,
but that's important for this argument.
Absolutely. Yeah. So,
but also for the even other precisely the same thing.
Yeah. So I tend to disagree that I can keep track of the origin of two vortices, and what you're saying is my scenario number one, that they've been keep being paired up in times and the interactions between ions that are not pulled out of the vacuum as a pair is negligible. So, well, one reason to think it this way is because of electrostatics, which could force them to form this pattern, and in that pattern you can no longer say which pair was originally, which pair of ions was originally a pair put on a vacuum. So what would be the experimental consequence?
If it was a completely uniform, the ideal being a crystal, except for one guy was stuck on a impurity, it was just slightly off. So that just forms some sort of defect in the middle of the liquid with its own little edge state or something.
Well, so in principle, you would think that doesn't make much of a difference because it looks like a weak perturbation, but your microscopic calculations are that it's not. Yeah. So if you actually exponentially vary interactions by moving this guy around, you have an exponential scale that is competing with the gap of this liquid, and so all kinds of weird things might be happening. Yeah? And in particular, what might be happening is exactly what you're saying, that you start nucleating two different liquids, this one and that one, in different patches of this conhole fluid, and then you would have an edge between this liquid and that liquid, which is the dominant edge being around, and that is one which is distinct from the edge between this liquid and the original SO2. So it's getting, you know, one level more complicated. So if we don't assume that that is what's happening, experimentally this is what would be happening. We would not see any change in the electric transport, which is the statement that you're sitting on the plateau. Yeah? So this is happening on the plateau. So electric transport remains unchanged. But what does change is heat transport, because we have an additional edge between the original quantum Hall liquid and this new nucleated one. This additional edge carries heat, and as such, we will see that there is more neutral mode that can carry heat at the edge of the sample, not in the bulk. And yeah, so probably that is something that we can hope to eventually observe in an experiment. While a scenario where we nucleate all kinds of different liquids because of strong random interactions would have a different effect. It would be bulk transport. So here are my conclusions. The effect of interactions on the collective state of localized non-abelian ions is a split degeneracy, and we can identify the state that is selected after the splitting of states in the quantum antibody problem. And what it is, it's a new topological liquid, so a new gapped quantum liquid, which is separated from the original one by an edge. And we think that this stuff might be relevant as we detune the magnetic field of the center of the quantum plateau. Sounds great, that's
Yeah, so if I follow your 2D analysis in the large scale limit,
yes.
that would take me to a state of the Heisenberg model in 2D.
Yeah. So yes,
Is the gap surviving that? Or?
it's a beautiful question, and so we have done this connection between the quantum antibody state in one dimension between minor one fermions and the Heisenberg state. So now it's of course a good question asking the same thing in 2D. So what is it happens for a Heisenberg spin, this antiferromagnetic interaction in 2D? Well, I get an neon state. An neon state is a gapless state, and it's gapless because there is a Goldstone mode. And the Goldstone mode, of course, comes from spontaneous symmetry breaking of a continuous symmetry. That continuous symmetry is SO2. Now, in the anionic case, if I have no ionic fermions interacting, there is no continuous symmetry, no obvious candidate at least. Yeah? So there is no reason to believe that I will break that in a continuous symmetry and get a Goldstone mode. And as such, probably the occurrence of an gapless phase, like in the answer, would be more exotic. Okay? And it seems to be exactly that what we find. We find a gap, okay? Which is the analog of the neon state in these anionic. But that gap, of course, depends on how much you break time reversal symmetry, which these systems do. And you might think that that is exactly, so the gap, the bulk gap of the liquid goes like 1 over k, because that's the strength of the symmetry breaking. So as you increase k, the bulk gap of the topological liquid goes down, the Goldstone mode comes down and becomes soft only in the limit as you take k to infinity, which would be in exact correspondence to what we have seen for the chains, that the transition, the qualitative transition of the quantum antibody system happens only as you take the limit, as you go to k to infinity, and this is what might be happening here in 2D as well. Now, we are not particularly good in calculating this bulk gap for large system and finite time scaling in these things, so remains a speculation.
But of course, in the spin case, you're rather easily perturbed into some kind of RTB state with its own gap.
Mm-hmm.
So is something like that possible for the anionic?
Well, so for these small k series, the bulk gap again would be large. So what our calculation on the 4/8 square lattice for the Fibonacci anions suggests that the bulk gap is of order 1. In the interaction is going to be exactly what you call J. So the pair splitting is J, and the bulk gap is also J in the quantum antibody problem. So that's a large gap. So and again, it's just by the definition that the gap is persistent, you're stable to all kinds of perturbations and other instabilities. Yeah, but you get more and more and more and more susceptible to these things as k is increased, and the bulk gaps, likely become smaller and smaller, and then you recover these physics again.
From what you said, does this have any effect at finite temperature? For example,
What?
just the finite temperature, what's the consequence? For example, could you have a apostolic Taurus transition, or is that altered by this anionic?
All of these statements are for zero temperature. Well, I haven't carefully thought about finite temperature, only to the extent that while this is an instability which is relevant at zero temperature immediately, the effect of finite temperature is that it smears that out to some extent, that it what brings this transition off from the middle of plateau to some finite value of it, because you have to compare that temperature to the scale of those interactions that they're calculating. But beyond that, I haven't thought about finite temperature.
But presumably you would want the temperature to be, well, like you said, at the scale of interactions, and you don't want these quasi-particles to be too close together, probably. So you actually would like the temperature to be much lower than the temperature of the original, the characteristic temperature of the original whole state that you're working with.
Yes.
Right?
Yes.
So that means, for example, that if you want to do those heat transport experiments that we're talking about, you have to stay below the temperature value.
Yeah. So this question should actually be redirected to Steve, because he can give you the answer. So he has calculated the phase physics, and so he can put that into context of the original gap. So probably they should answer another.
Yeah, we can estimate. We can estimate number, depending on the
Maybe a stupid question, but what stabilizes physically the edge? Because if you have quasi-particles which have either repulsive or attractive interaction, how can you have an edge?
Yeah, so edge physics is something that is omnipresent in these topological liquids. It's protected by the topology of the system, basically. So the fact that you have two distinct gapped phases touching, so two gaps close, that's where the edge lives, So you cannot get that out without making a direct phase which is possible between the one and the other phase, but because they are distinct, that is not possible. And as such, the critical mode in between.
I was just thinking more physically, because you're talking about like a weaker crystal or long-range interaction that stabilizes the crystal. So if it's a long-range repulsion, it always pushes the edge away.
No, but so this is a slightly different physics. But what stabilizes the Wigner crystal is a different interaction than the one which is responsible for this edge. So the Wigner crystal is stabilized by electrostatics, which is coupling to a different quantum number, the charge of these excitations, while this happens in the non-abelian sector. So in the context of ordinary solid-state physics, this abstraction is similar to when you say that in a solid you have electrons and certain orbitals that carry spin, and you just talk about what happens in the spin sector, and this is what I'm doing here. So I'm talking about what happens in the non-abelian sector, and it's this. And in the solid, you might also ask, well, just describe the spin model for the solid, but you didn't take into account the charge degrees of freedom, and oftentimes we don't need to. And so this is a similar level of abstraction, that what stabilizes this lattice is taken for granted and not further considered, and then using the lattice you're doing a calculation.
Yeah, well, I was just thinking your model of the quantum Hall liquid, because I don't see there how the voltage lattice or anything can be stabilized by some edge.
No, it's not the edge that stabilizes the lattice.
No, but I mean, how can the edge be there? How can one region be different from other? Because the quasi-particles have a repulsive interaction.
Well, so at the end of the day, this edge is actually pushed to the edge of the sample.
Okay.
So
that's what I mean. That then the edge of you don't have two different liquids.
Exactly. So yes. So what it means is actually that eventually you will push out the original liquid completely, and so that liquid is soaked. So this blue liquid is actually gone, and the edge lives on the edge of the sample, where it adds
but
to the edge.
But then you can't really talk about the edge of the blue liquid.
No, that's not true. Okay. So the blue liquid has an edge itself to the vacuum, the white stuff here, which carries heat. Okay. Now you put a second edge out there, and you get just more edge modes. So that's.
But maybe it's helpful to say that you can also have local density variations, or even induce local density variations with fields, and then you'll have different Fourier fractions in different parts of the sample, and then you will have this.
Oh boy. Yeah.
Probably.
But then your edge is not sharp anyway.
So this is an important thing to say. So we are not considering different Fourier fractions, and we are not considering a hierarchy construction when we do any of this. Yeah? So we always, try to stay at the same filling on the same plateau.
But I didn't mean to say it's in different plateaus.
No, yeah. There is a sort of confusion that might be worth saying that.
So back to this question of charge versus topological degrees of freedom.
Yeah.
I mean, the pictures where you have a perfect figure lattice, and then then you're done with that, and then you do topological degrees of freedom. But in fact, you could imagine having coupling between the two, because once it's more attractive in one channel than the other, and then they sort of jiggle around a little bit depending on the channel they're in. And there's some sort of, is there some limit in which you can show that that doesn't do anything?
Well, all that is microscopic at the end of the day. So it involves calculation of yours in order to make any quantitative statement or qualitative statement at all. If the jiggling is having no dramatic effect of the interactions, nothing is supposed to be happening. If it has a sensational effect of the interaction because there's exponentials involved, then all kinds of weird things might be happening. So this makes the microscopics in quantum Hall quite different from the microscopics of spins in solid state where there's no exponential decays of interaction typically, so the small wigglings don't have a dramatic effect. But it looks like this is happening here, which is both a curse and a blessing. Blessing in the sense this might be a cool system to study infinite randomness, but it's put in per se and not an abstract limit.
More questions? No, let's set up the
It's funny, like, No, I have looked at
essentially is what engineering topology. Usually you have some LA states involved, states involved why you
The red flux.
Oh,
okay. Flux is tied to the charge. Sort of. There's some puddle of charges here. But there's some region where there's some preference to be at exactly 1/3. Now, the preference is there's some strip. Then you add
oh no, you're
but I think the thing is, the thing to do is is to really make it perfectly
Yes, exactly. So today I started I take a few electrons, the same and put this number of electrons, one spot of circuits. But then if you order there.
Yeah, so you're right. You will to be a lot of those quasi-particles in the puzzles. And that will satisfy something that's very satisfy all the electrons.